So far, we have looked at conduction and convection, and both of these methods needs particles to transfer heat. But heat managed to get us from the sun, and there's definitely no particles in space. It's a vacuum. So how does the heat from the sun gets to us? Well, it travels as rays for heat transfer of radiation. We can actually find different colors are better at emitting heat than others. Now, all hot objects emit heat radiation, and this is a physics term of hot. What is essential means is any object above 0. Anything above that emit heat, however, it will also be absorbing heat radiation, and it's only if it is hotter than the surrounding that's it's actually going to be emitting heat overall. So it is actually, let's first look at the silvery shiny side. I mean, see, there is a really bad at emitting radiation. There's hardly any waves coming out of there at all. We then turn to the white shiny side. You see, there is only marginally better, still pretty bad at emitting radiation. The matte white side, slightly better, still pretty bad at emitting radiation. The matte white side, slightly better but pretty bad. Let's go around to the shiny black side, and we see all of a sudden there is emission of a fairly bit of heat. But now if we turn around again, we see the matte heat. But now if we turn around again, we see the matte. We can see that is going like crazy, that is emitting off lots of heat radiation, and we can see from that matte black is the best color at emitting heat radiation. So what color is going to be the best color at emitting heat radiation? So what color is going to be the best at absorbing heat radiation? We have seen that matte black is the definitely best emitter. So the matte black falls off way in advance of the shiny silvery surface. It is because matte black advance of the shiny silvery surface. It is because matte black is absorbing all that radiation, but shiny silvery is reflecting the radiation. So the key information that we get is a brief information about the thermal radiation, and we come to know that when heat need to be thermal radiation, and we come to know that when heat need to be transferred across a vacuum, the only way it can do it by radiation. We have also seen that matte black is the best absorber and emitter of the radiation. That is why if we want something to heat up really quickly and something to cool down, we used to want something to heat up really quickly and something to cool down, we used to color it by matte black. Black body radiation is the radiation produced by heated objects, particularly from a black body. A black body is any object that absorbs all radiation, for example, visible light, infrared light, ultraviolet light, etc., that falls on it. This also means that it will also radiate all frequencies that heat energy produces in it.
The characteristics of blackbody radiation can be described in terms of several laws. Number 1. Planck's law of blackbody radiation, a formula to determine the spectral energy density of the emission at each wavelength at a particular absolute temperature. Number 2. Wien's displacement law, which states that the frequency of the peak of the emission increases linearly with absolute temperature. Conversely, as the temperature of the body increases, the wavelength at the emission peak decreases. Number 3. Stephen Boltzmann's law, which relates the total energy emitted to the absolute temperature.
The Earth's surface is a source of thermal radiation as it absorbs energy received from the Sun. The wavelength of this radiation lies in the long wavelength infrared region. But a large portion of this radiation is absorbed by greenhouse gases, namely carbon dioxide, methane, nitrous oxide, chlorofluorocarbon, and tropospheric ozone. This heats up the atmosphere, which in turn gives more energy to the Earth, resulting in warmer surface. This increases the intensity of the radiation from the surface. The net result is heating up of the Earth's surface and atmosphere. This is known as greenhouse effect. Without the greenhouse effect, the temperature of the Earth would have been minus 18 degrees Celsius. Concentration of greenhouse gases has enhanced due to the human activities, making the Earth warmer. Because of global warming, ice caps are melting faster, sea level is rising, and weather pattern is changing drastically. Many coastal cities are at the risk of getting submerged. The enhanced greenhouse effect therefore also results in the energy of radiation emitted by a black body should increase with temperature. On the basis of these considerations, we come to the conclusion that the total energy of radiation emitted by a black body is proportional to a monotonously increasing function of thermodynamic temperature only. While greenhouse gases keep our planet livable by holding on to some of Earth's heat energy so that it doesn't all escape into the space. Thus, we conclude the project. This was a group initiative of Satakshi Bhattacharya, Srijan Banerjee, Rohit Shaw,